Hi. In this video, we're going to go through some worked problems on vector and matrix multiplication. A little bit more involved than the last set of worked problems in scalar addition or scalar multiplication and matrix and vector addition. So we're going to start off with some operations involving vectors, a pair of vectors u and v. I recommend that at this point you pause your video and work through these, or attempt to work through these four problems given, evaluate these operations given u and v. After you've had a chance to try to work through them, then continue to look at the completed solutions, the work solutions. Okay. So let's consider this first one. This first one is just a simple dot product to get us started. The dot product of u and v. How do we evaluate a dot product? We multiply together corresponding terms and then add all of those products up. So 1 times 1 plus 0 times -1 plus 3 times -1. The first product, 1 times 1, gives us 1. The second gives us 0. The third gives us -2. And the sum of all of those gives us -1. Right? Fairly straightforward. Most people don't have too much trouble remembering dot products. Second problem, the norm of v. Remember, this notation of 2 bars on either side of a vector indicates the norm, sometimes called the 2 norm, the Euclidean norm, which is, in geometric terms, the length of the directed line segment corresponding to that spatial vector. And the way we evaluate the norm is by taking the square root of the dot product of the vector with itself. We do not need that extra plus sign there. Okay. There we go. All right, so start by evaluating the dot product of v with itself. This is simply the sum of the square of each individual term. As the product of each individual term with itself, each individual element with itself. 1 squared plus -1 squared plus -1 squared. Looks like there's a couple typos on this that I'll fix in the notes. This should be a negative. There we go. All right. Sorry about that. With those typos corrected, 1 squared plus -1 squared plus -1 squared, 1 plus 1, 3. So the norm of v is the square root of 3. Another dot product, but this one where we've combined scalar multiplication, addition, differences of vectors together with applying the dot product. Rules of precedence are the same as we are sort of generally used to. The operations within parentheses are done first. So the first thing that we do is we evaluate this expression inside the parentheses and this expression inside parentheses. 2u plus v, scalar multiple of 2 times u, plus v, scalar multiple 2 times 102 is 204. and then adding to that 1, negative 1, negative 1 gives us 2 plus 1, 0, negative 1, 4 minus 1, or 3, negative 1, 3. This is the first vector of our dot product. The second vector, u minus 2v, we compute in the same way. 2v would be 2, negative 2, negative 2. So u minus that, 1, 0, 2, minus 2, negative 2, negative 2. 1 minus 2 is negative 1. 0 minus negative 2, or 0 plus 2 is 2. 2 minus negative 2, or 2 plus 2 is 4. So the dot product we want to evaluate is the dot product of the vector 3, negative 1, 3, and the vector negative 1, 2, 4. Multiply corresponding terms and add them up. 1 plus times negative 3 plus negative 1 times 2. Oops. I apologize for these typos. Plus 2 there. Negative 1 times 2 plus 3 times 4 is negative 3 minus 2 plus 12, which is 7. Okay. A little bit more involved in terms of the arithmetic, but the underlying ideas are not anything new. Scalar multiplication of a vector, addition of vectors, and evaluating a dot product. Just walk through them systematically. The last example, combining a vector difference with a norm, we take exactly the same approach. First, compute the difference of the vectors, v minus u, 1, negative 1, negative 1, minus 1, 0, 0. Take a difference of corresponding terms. 1 minus 1 is 0. Negative 1 minus 0 is negative 1. Negative 1 minus 2 is negative 3. Then we're ready to evaluate the norm. The norm is the square root of the dot product with itself. So we calculate the dot product of the vector we just computed with itself. Sum of the squares of corresponding terms, 0 squared plus negative 1 squared plus negative 3 squared. 0 plus 1 plus 9 is 10. So the norm of this vector is the square root of the dot product of that vector difference with itself, or the square root of 10. All right. So now moving on to some matrix products. I've given 3 matrices, A, B, and C. Note that they are different sizes. And a set of vector products that we'd like to try to evaluate. Take a moment again, pause the video, try to work through these products to compute them. If you're unable to, explain why it's not possible, why you're unable to compute them. Right. All right. So let's go through these. The first, we want to compute the product AB, where A is a 2 by 2 vector matrix, 2, negative 1, 0, and 1. B is a 2 row by 3 column matrix. This is a valid product because the inner dimensions match. A is a 2 by 2 matrix. B is a 2 by 3 matrix. These two inner dimensions are the same, so they match. That means we are allowed to evaluate the product. And when we do so, those inner dimensions are going to disappear, and the answer that we get should be a 2 by 3 matrix. The way we find the elements of this resulting matrix are by walking along rows of A and columns of B and taking the corresponding dot products of those vectors. So we're going to start off with filling up the first row of this vector. The first element of the first row, we start with the first row of A and the first column of B. And we take the dot product of those. 2 times 1 minus 1 times 2, right? Sum of products of corresponding elements. Of course, 2 times 1 minus 1 times 2. 2 minus 2 is 0 for that particular piece. Then, again, we work with the first row of A to find the second element of the first row of the product. And we take the dot product of that first row of A with the second column of B. 2 times 0 minus 1 times 2 is 0 minus 2, or negative 2. Continuing this process, first row of A, third column of B. 2 times negative 1, negative 1 times 1 is negative 2 minus 1 is negative 3. That completes the first row of the product. To get the second row of the product, we start with the second row of A, and we do the same thing. Second row of A with the first column of B. 0 times 1 plus 1 times 2 is 0 times 2. 0 plus 2 is 2. And we carry along with the same process to complete the second row. Second row of A plus the second column of B, 0 times 0 plus 1 times 2 is 0 plus 2 is 2. And 0 times negative 1 plus 1 times 1 is absolutely not what is written down here, is 0 plus 1, which is, of course, 1. All right. Okay. This is, I went through this fairly slowly just to get us sort of extra familiar with how we do these matrix products. In this example, we have a second problem. We have another matrix product, C times B. We do a quick check to make sure that it is allowed. C is a 2 by, is a 3. Let me just erase that and start over. Is a 3-row by 2-column matrix, and B is a 2-row by 3-column matrix. The inner dimensions are both 2. That is, the columns of B and the rows of, the columns of C and the rows of C and the columns of B match in number. They are both 2. They match so we can evaluate the product. They will disappear in the product, and our answer is going to be a 3 by 3 matrix. Okay. Let's now go through and evaluate this. I'm going to do this one a little bit more quickly than the first one because we've already gone one product in detail. To complete the first row of this 3 by 3 answer, we work with the first row of C and then each column of B. First row of C and the first column of B, -1 times 1, plus 3 times 2 is -1 plus 6 is 5. First row of C and second column of B, -1 times 0 plus 3 times 2, 0 plus 6 is 6. First row of C, third column of B, -1 times -1 plus 3 times 1, 1 plus 3 is 4. For the second row, we move down and do the same thing, but with the second row of C. First column of B, 1 times 1 plus 0 times 2, 1 times 0 is 1. Second column of B, with the first row of C, 1 times 0 plus 0 times 2 is, of course, 0. And with the third column of B, 1 times -1 plus 1, 0 times 1, -1 plus 0 is -1. Finally, the third row, we are going to do the same thing. We work with the third row of C, multiplying each of the columns of B. And here we actually note that there's a little trick that we can take advantage of that can speed things up. The first row and the third row of C are identical. If the first row and third row of C are identical, when we go through taking dot products of the row with each of the columns of B, we have to get exactly the same result, which means the last row in the product has to look exactly the same as the first row in the product. If you were unsure about your arithmetic, you could go through and do the arithmetic again. That would serve as a double check that these two rows better end up the same, or else a mistake was made. If you're confident that you didn't make any arithmetic mistakes in that first row, simply copying that first row to be the third row of the product is a speed up we can take advantage of. Okay. So now we have a triple product, A times B times C. Right? For multiplying matrices, it doesn't matter what order we evaluate the product, as long as we don't rearrange where the matrices are. That is, we could multiply AB first and then multiply by C, or we could multiply by BC first and then by A here, and this should be better, written as A, B times C, is the easiest product for us to evaluate because we've already computed AB. Since we've already computed AB, to get this product ABC, all we need to do is take our answer from the first example and now multiply it by C. Quick double check that the dimensions work out. We see that AB is a 2-row by 3-column matrix. C is a 3-row by 2-column matrix. The inner dimensions match, so they will disappear in the product, and we should be ending up with a 2-by-2 matrix as our answer. We evaluate that exactly the same way, working through either, first of all, the first row with each of of AB, with each of the columns of C, and then moving on to the second. Adding up the product of corresponding terms in each time. 0 times -1 plus -2 times 1 plus -3 times -1, 0 minus 2 plus 3 is 1 for the first element of the first row. 0 times 3 plus -2 times 0 plus -3 times 3, 0 minus 9, -9 for the second entry in the first row of the product. Moving on to the second row, 2 times -1 plus 2 times 1 plus 2 times 0, -2 plus 2 plus 0 is of course 0. And the second entry on the second row, 2 times 3 plus 2 times 0 plus 0 times 3, 2 plus 0, 6 plus 0 plus 0 is 6. Our product ABC. All right. Let's move on to one more example. A times CB. Here, we've already computed CB, and so we may attempt to do this by evaluating the product A times CB, as we have here. Since we already have CB, but if we take a look at our quick analysis of dimensions, we'll see this fails. A is a 2-by-2 matrix, CB is a 3-by-3 matrix. These two inner dimensions do not match. We cannot evaluate that product. Now, we were trying to evaluate this using the pre-evaluated product CB, so that's the comparison we made. If we hadn't done that, if we were just given this question before having done any other work and we were sort of thinking about where to start, even before multiplying any of the matrices, we need to do this, we should do a check, and we can do this simply by looking at the dimensions of all of them, right? A times C times B, writing out their dimensions. A is 2-by-2, C is 3-by-2, B is 2-by-3. In order for this triple product to be well defined, the two pairs of inner dimensions both have to match. And in this case, one of them matches. That's why we were able to evaluate CB in the earlier example. But this one doesn't, as long as one of the pairs of inner dimensions is inconsistent, that's enough to make the whole expression undefined. If you forgot to do that, if you forgot to do the check, you would very quickly realize, or you should very quickly realize, that something is wrong. If we try to evaluate this product, what would we try to do? We would try to walk along the first row of A and the first column of CB, multiplying corresponding entries. And so we would say 2 times 5 plus -1 times 1 plus, but then what do? We have another entry here. We don't have a third entry. We can't complete this expression because of the mismatch in the dimensions. It's usually quicker just to do the check, to quickly look through all of the dimensions and see, is this something I'm allowed to evaluate or not? If you forget to do so, and you hit something that looks like a problem like this, use this as a flag. Okay, something's going wrong. Let me go back and just double check. Am I even allowed to be doing this? Because if you're not, and you try to do it anyway, obviously you're going to get into trouble. Okay, that wraps up our set of worked examples on matrix products, on simple numerical matrix products. There's a second set of worked examples where we go through using the matrix product with variables to express linear systems of equations in terms of matrix products. Thank you and goodbye.